In the real world, objects rarely move in perfectly straight lines, and forces like gravity or wind often vary depending on your location. To calculate work in these complex scenarios, we must use the power of line integrals. A vector field assigns a vector to every point in space. Think of it as a map of forces. At any specific coordinate, the field tells us exactly how much force is acting and in which direction it is pointing. To integrate over a path, we first parameterize the curve. We describe the path using a vector-valued function, r of t, which traces the trajectory as time progresses from an initial value a to a final value b. By summing up all these tiny bits of work along the entire curve, we arrive at the line integral. This formula translates the physical concept of work into a definite integral that we can solve using standard calculus techniques. The dot product is crucial. If the force and motion are in the same direction, work is positive. If they are perpendicular, no work is done. If the force opposes the motion, the work is negative, indicating energy is being removed. Let's calculate the work done by the field F equals y, negative x along a quarter circle. First, we parameterize the circle using sine and cosine, and identify our limits of integration from 0 to pi over 2. Next, we substitute our parametric expressions for x and y into the vector field. We also calculate the derivative of our path, r' of t, which represents the velocity vector at any point along the curve. Now we compute the dot product of the field and the velocity vector. In this specific case, the components simplify beautifully using the Pythagorean identity, leaving us with a constant value of -1 to integrate. Integrating -1 over the interval gives us a total work of -pi over 2. The negative sign confirms that the vector field was generally pushing against the direction of our movement along the quarter circle. Consider a constant gravitational field acting downward. We want to find the work done as an object slides down a ramp. Even though the path is diagonal, only the vertical component of the movement will contribute to the work. In special cases like gravity, the work done depends only on the starting and ending points, not the path taken. These are called conservative fields. For these, the line integral is simply the change in potential energy. However, not all fields are conservative. In a non-conservative field, like one representing friction or magnetic forces, moving in a complete circle might result in non-zero work, meaning energy is lost or gained over the loop. To recap, always follow these 5 steps: parameterize your path, find the derivative, substitute into the vector field, calculate the dot product, and finally, evaluate the definite integral over your time bounds. Line integrals are the mathematical tool for measuring how much a vector field helps or hinders motion along a specific trajectory. This is the fundamental way we calculate work and energy transfer in physics. Think about this: if a force is always perpendicular to the direction of motion, like the tension in a string during circular motion, what is the total work done? Based on the dot product, the answer must be 0. Mastering line integrals allows you to solve complex engineering and physics problems involving variable forces. You now have the tools to calculate work along any path in a vector field. Generated by Vision Solve AI.